Welcome back, Chemistry 30. This is the second part of the MS 2.1 section. So we just went through this chart, went over molecules that are likely to be polar versus non-polar. You can use this little scheme here to see if a molecule is symmetrical or not. And of course, this works if the outer elements are identical and when the electronegativity difference is large enough. Now, if the electronegativity difference isn't large, such as it falls way less than that 0.4 fringe number, then all of these will be non-polar. We won't even have to worry about this chart. The only time we have to worry about this chart is when that electronegativity difference is large, giving us polar bonds, and then from that we see overall, do those polar bonds neutralize each other or do they combine in a particular direction? So that takes us to this next part here, in which we'll do some examples and see, in fact, whether we have polar bonds, and if we do, what happens to them. So we'll look at these examples. So again, it's just like what we've done before. We're just adding a little bit extra onto that. So bromium and chlorine. Now, this is a linear shape. Even though it's made up of two atoms, there's no central atom. We still refer to this as linear. These are both group 7. So there's one bromine and one chlorine. The bromine will have 7 valence electrons. The chlorine has 7 valence electrons. So that's going to give us 14 valence electrons in total. All right. So in drawing that out, bromium attached to chlorine. Put the extra electrons on the outer edge. 2, 4, 6, 8, 10, 12, 14. I have 14 electrons there. And if we do the formal charge calculation, these are both group 7s. And 1, 2, 3, 4, 5, 6, 7. And then they both have 7 electrons involved in the structure. So that is definitely what the structure looks like. And then we should look at is this going to be a polar bond or not? So, of course, in order to do that, we have to take out the electronegativity sheet and look at the chart that we made on the flip side. And I made my chart just on a separate piece of paper that looks like this. I'm not sure what you did, but that's what we did. And if you look at bromine and chlorine here, so bromine's 2.96, chlorine's 316. 316, and then 2.96. So if we subtract that, 3.16, subtract, so yeah, you can see these are very close to each other. So what do I get there? I get 0.2. Yeah, so 0.2, that falls into the category of less than 0.4. So for all intent and purpose, we have equal sharing there. So I can say non-polar bond. And therefore, I don't have to worry about using anything else. The overall molecule is going to be non-polar. Non-polar molecule. And of course, if we do have a central atom, we'll do all the other material that we did with our other examples and figuring out the shapes, etc. But this one we can just simply take as being linear. All right, next one, SO2. So SO2, we have 1 sulfur, 2 oxygens. Those are both group 6 elements, so they have 6 valence electrons. So we'll have 6 and 12, so it's going to give us 18 valence electrons. I think we've drawn this one before. So if I draw it, okay. So we have that, 2, 4, 6, 8, 10, 12, 14, 16. There's an extra electron set, so we put it by the sulfur. Then, of course, we have to go through the formal charges. So each of these is a group 6 atoms, and 1, 2, 3, 4, 5, 6, 7. Oh, we have a problem here already. And then 6 minus 1, 2, 3, 4. So the sulfur is too short, the oxygens are too high, so we're going to have to donate a pair from the oxygens to the sulfurs. Or sulfur, I guess there's only one. So 2, 4, 6, 8, 10, 12, 14, 16, 18. I still have 18. If I do the formal charge calculation, you can see that we have 6 here, so we're good here, which means we're going to be good over here because it's identical. And then sulfur, 1, 2, 3, 4, 5, 6. Good. So we're good there. Now, of course, here state the number of electron domains. So domains here. What do we got here for domains? We have an area of electrons here, here, and here. So the electron domains around the central atom, around the sulfur, are 3. So if we look at electron domain geometry and molecular domain geometry. So 3 domains. So if we look at 3 domains, the default, if all those were important, it'd be trigonoplanar. So if I take all those electrons contributing to the shape, trigonoplanar. But if I look at what I actually have here, I have 2 bonding and 1 non, and again, the double bonds is simply count as a bonding area, period. 2 bonding, 1 non-bond. Where are we at here? So 1 bonding, or 1, this chart has it in terms of how many are non-bonding. Domains of 3, 1 non-bond. Domains of 3, 1 non-bond. And you can see it looks very similar to that. It is a bent shape. And of course, bent, there's a potential that it could be polar. The only thing I have to do is check to see, is that electronegativity difference large enough? So if I look at the numbers, let me get a different color here. Sulfur is 2.58. So 2.58. And oxygen is 3.44. All right, so I'm going to look at that difference to see what do I have there. So 3.44 minus 2.58. Okay, borrow from there, A5, let's see here. So what do I get there? I get 14 minus 8, which is 6. Borrow 1 from here. I almost forgot how to do that. 0.86. 0.86. So where does a difference of 0.86, where does that fall? 0.86. It's a polar covalent bond. So there will be a pull in these directions. Now what I should show here is that, so the oxygen is definitely going to pull the electrons in its area more often. So I could show that with that. So show the poles in those bonds. And of course that leaves sulfur slightly positive and each of the oxygens slightly negative. They aren't going to balance each other out because there's a pull. Because again, the shape of this molecule is not linear. It's bent, so there's going to be a pull in the downwards right, pull in the downwards left. Those will combine to be a somewhat downward pull. So it will be polar. So I can say that is going to be a polar molecule. Oh my gosh, how did I spell that? Polar molecule. And over here I could have said something. These are polar bonds. Okay? And that leads to a polar molecule because they do not balance each other out. There is no balancing there. There is a pull in a particular direction. Right, let's look at the last one here. So let's look at SF6. Get my color back here. SF6, so sulfur, hexafluoride, so sulfur is a group 6 atom. Oops. So I have, let's see, I have 1 sulfur and 6 Fs. F is a group 7. So here I get 48 valence electrons. All right. So the S is attached to an F, so we can see what kind of shape this is. 4 more here. So that one's kind of behind, this one's in front, this one's behind, this one's in front. And then put those around. So it's kind of hard to draw it three-dimensionally, but we can kind of envision it as being so. 1, 2, 3, 4, 5, 6. So each of these is 8. 8 times 6, 48. That's what it should look like. So in terms of domains, there are 6 electron domains, because there's 6 areas around that sulfur where we have attachments. Then we're going to look at electron domain geometry and molecular domain geometry. So if I look here, so I have 6 domains. They're all bonding, so octahedral, and of course the molecular domain is the same as well. I don't have any lone pairs, so it's going to be octahedral as well. Now, of course, here, if it's octahedral, it'll be nonpolar. So no matter what will happen, even if there is a pole, all those poles will balance each other out. But we still need to show that calculation. So if I look over here, fluorine I know is 3.98, right? That's the largest one on the table, 3.98. So all these are 3.98. An individual sulfur is 2.58. So 3.98 minus 2.58. So that's 0.4. So 1.4, that's definitely a polar bond. It's in between here. It's a polar covalent bond. Polar covalent bond. But since it's symmetrical, so I could show this. There's a pull in this direction, a pull in this direction, a pull in this direction, a pull in this direction. Pull in all, so I have a pull in every single direction, but guess what? They balance each other out, but non-polar molecule overall. Because it balances each other out. And again, I'm just using this sheet again. These up and down cancel, these two cancel, these two cancel. So that's how that comes together. All right, so I'm going to stop there. And what you can do is look at the next page, because I believe there are a couple of more questions there that you can try out. There's 2 more, I believe. Here they are. I had to find it. NF3 and BCl3. So I'll get you to try those, then tune into the next video to see how you made out.